analysis, Bernoulli convolutions. So let me just very quickly recall the setup. Nu lambda. So we consider this random variable, which is plus minus, lambda times epsilon 1 plus lambda square times epsilon 2 plus dot dot dot, where lambda is some fixed number, okay? And epsilon is a random, plus or minus 1 with equal probability and independent of each other. So the distribution of x lambda is what we call nu sub lambda. And sums of independent random variables correspond to convolution. So it is the infinite convolution of these Bernoulli distributions. Bernoulli is a general phrase to say that it's supported on 2 points. So you have symmetric Bernoulli distribution supported on lambda and minus lambda, lambda square and minus lambda square, and so on. So it's the infinite convolution of that. And what we will use, and it's a very useful point, another way of characterizing it also is via the Fourier transform. Since it's a convolution, the Fourier transform is a product of the individual Fourier transform. So we see that nu lambda hat of t is the product of cosine lambda to the n t. So this is the Bernoulli convolution. As I explained, there are more general Bernoulli convolutions you can consider, where instead of lambda, lambda square, you can consider any a1, a2, a3. Instead of an exponentially decreasing sequence, you can consider more general ones, but we are sticking to this particular case. Now, I also mentioned that this infinite product converges and it doesn't vanish unless one of the terms vanishes. So that is a general fact that which we will use, that when you have a product and let's say an's are real numbers less than 1, less than equal to 1, unless one of them is equal to 0, the product can't be 0. This is all under the assumption summation an is finite. Okay, so that's the thing. And then our main question was, is nu lambda singular or absolutely continuous to Lebesgue measure? And we know 2 special cases are perhaps familiar. One is half. You get the normalized Lebesgue measure on -1, 1. This is, as I said, corresponding to the fact that if you pick a uniform random number, its digits in the binary expansion, or any expansion actually, are going to be IID random variables. Okay, so. And when lambda is 1/3, this is actually the Cantor measure, except that everything is shifted or affine transform to -1, 1 instead of 0, 1. So the question of whether it's absolutely continuous or singular, that question, first easy thing that we did was for lambda less than half, nu lambda is singular because you can even put the support inside a set of 0 measure. So we did that. I don't want to recall that. So for lambda less than half, it was singular. For lambda equal to half, it is absolutely continuous because it's Lebesgue measure itself. So question is, what happens for lambda bigger than half? And there, the natural expectation would be to that, okay, maybe it will become absolutely continuous. It was singular to start with. Now it becomes absolutely continuous, maybe. But that is not the case. So, well, before that, okay, another point that I said was this nu lambda is always absolutely continuous or singular. It doesn't have a mixture of absolutely continuous and singular parts. This is coming from the self-similarity property, that the fact was that nu lambda was the unique probability measure with a certain self-similarity property. And so if it had an absolutely continuous and singular part, both of them would have the same property. So this is a point that I should have said first. It will be either absolutely continuous or singular. So the question, is it absolutely continuous or singular, should have a clear-cut answer, one way or the other. It can't be neither and such things. So what happens for lambda bigger than half? The natural expectation may be to see that it might be absolutely continuous, but in fact, it's not. And this is what I was saying, that errors showed that there are countably many lambda for which it is actually singular. Okay. So let's go over that. So what are these exceptions? So they are the reciprocals of these piezo-Vijayaraghavan numbers. So that's the theorem that I come to now. Okay. So I'll just finish the recap by recalling the PV number. PV numbers are algebraic integers. Algebraic integer means they satisfy an integer polynomial. So it's the zero of an integer polynomial. Monic integer coefficient polynomial. It's a PV number if theta itself is a big number bigger than 1, but all the other roots of its minimal polynomial are of absolute value less than 1. Okay, so those are the conjugates of theta. So these are numbers. So there are many examples of that. There are countably many. So one example I gave is the golden ratio, because it is the root of x square minus x minus 1 whose other, this is a number bigger than 1, whereas its other root is number absolute value less than 1. So this is a piece of Vijayaraghavan number. Okay, so you can take the reciprocal of this. So this is somewhere between 1 and 2, I think. So square root 5 is about 2 point something. So 1 plus 2 point something is 3 point something. So when you divide by 2, it is between 1 and 2. So its reciprocal is between half and 1. So those are the numbers for which nu lambda is going to be singular. Okay, I showed that for all lambda which are reciprocals of piece of Vijayaraghavan numbers, this nu lambda is singular. Now, as I mentioned, no other examples are known in this range for which it is singular. Okay, so this is Erdős paper was 1939, I checked. So it is like 60, 80 years now. But okay, so I wanted to, let me first continue, just since I did the recap, let me just continue and prove this, prove the proof of Erdős theorem. What happened here? Before that, are there any questions or comments? If some definitions.
Oh no, you might have mentioned this earlier, but how hard is it to show that it's almost everywhere it is in this range? It is absolutely continuous, because your some tools are there. So.
No, that is, I will come to that question. Actually, I was thinking whether to do that also. Well, let me come to that after the, so that proof itself, I don't know. But I have read Erdős proof, which is that it is almost surely absolutely continuous, not on half to 1, but on some interval 1 minus delta to 1. That is reasonable. Still,
okay.
I am not yet decided whether I want to present it. Maybe I will not. But
okay.
I'll come to the
no, but just want to know how hard it is. Is it because you have okay?
No, it is very much true. In fact, it is something that I can even cover in the lecture. For the half to 1, it is a bit more. I mean, it's also not a long paper. There are two proofs. One of Solomiak, who was the one to actually prove it, using Fourier transforms again. And then there is a simpler proof. They say simpler proof. I have not read either of these by Yuval Perez and Solomiak. That doesn't use Fourier analysis. That uses differentiation of measures. So these proofs are not super difficult either. Meaning they were open for a long time, but once you understanding the proof is not difficult. Yeah. Let me say I don't know those two proofs, but the Erdős proof is very much something that I more or less understand now. I'm still, but it has a few steps which I don't know whether I want to do or not, etc. But after this proof, I will come to the absolute continuity. I will show something. I'll state some things. We'll see. Okay.
Okay. Thanks.
Yeah. Okay. Any other questions, comments, or anything on this? Okay, so what we want to prove is let's fix lambda equals 1 by theta, where theta in 1 to 2 a PV number. Okay. So what we will show is we will consider nu lambda hat. We want to show nu lambda hat does not vanish at infinity. That means you have to show find a sequence going to infinity where on which it doesn't vanish, right? So it is not that, I mean, along some sequences it may go to 0, but not vanish at infinity means there's one sequence on which it doesn't go to 0. So what is that sequence he considers? So here is the clever part. So you may recall nu lambda hat of t is product cosine lambda to the n t. So what is the sequence of t that you will consider? So Erdős considered the sequence 2 pi theta to the k itself. So consider a number of the form 2 pi times theta to the k. Theta is bigger than 1. So this is going to infinity as k goes to infinity. So what is the point? This is product cosine 2 pi. See, this is 1 by lambda, right? So this is 1 by lambda to the k. So this is lambda to the power of n minus k. Sorry, n equals 1 through infinity. So did I want to write like this? No, let me write it in terms of theta. That is better for me. So lambda is 1 by theta. So let me just write it in terms of theta. So 2 pi theta to the k and then lambda to the n. So it will be theta to the k minus n. N equals 1 through infinity. So you can divide it into two parts. So let's do n equals. See, so what is happening to this power? So it starts with theta to the k minus 1 and goes up to theta and 1 and then it goes to 1 by theta square and blah blah blah. Okay, so this part is actually, so let's take just the first part, n equals 1 up to k, you get cosine of 2 pi theta to the, I can write theta to the n because that's what comes, right? Theta to the 0, theta to the 1 up to theta to the k. So that comes. And what is the remaining part? The remaining part is 1 lambda lambda square. So that is just nu lambda hat of t. Okay. So what I mean here is that, so you take the, divide the product from n equals 1 to k and then product n equals k plus 1 to infinity. So this is just cosine 2 pi lambda to the power of n minus k. Here, theta is lambda and theta reciprocal. So lambda to the n minus k. Here it is cosine 2 pi theta to the k minus n. And maybe I'm over explaining, but the point is this is just this is n minus k starts from 1 onward. So this is just nu lambda hat of t. Whereas this one k minus n goes from also 1 to k or something like that. So this is actually cosine 2 pi theta to the n equals 1 up to k. Okay, so can I guess this? So the second part is.
Sorry, wait, what is t? T is 1 by theta.
T is just, no, sorry.
No, what is it? 1.
T is just okay. Sorry.
2 pi.
2 pi.
Something. Yeah.
It is just 2 pi, right? Nu lambda hat of 2 pi. Sorry, that's what I should have said. It is just nu lambda hat of 2 pi. I think that is all I want to say. Yeah, nu lambda hat of 2 pi. Okay. 1 second. Should I worry about that? Where does nu lambda hat vanish? I don't want it to be a place where it vanishes. So we wrote where nu lambda hat vanishes, right? So where is that?
That's like 1 by odd multiples. Yeah.
Okay. So 2 pi nu lambda hat of 2 pi is not 0. Right? That's all I want. So, okay. So that I will come to. So that part, I don't want that to be 0. Otherwise, I mean, I want to show this doesn't go to 0. It would be foolish if this is 0. But if that is 0, all you will do is you will just multiply this whole thing by one number t. That number t will go in here also. But okay, anyway, we don't need to worry about that. Nu lambda hat of 2 pi is not 0. Because I argued that nu lambda hat of t vanishes only at in the things that are of the form 1 by lambda to the n times odd multiple of pi by 2. Now 2 pi is not of this form. It's not an odd multiple of pi by 2. So it's not like that. And theta is anyway a rational number. So that's okay. So we observe. So this is not 0. Now what happens to this thing? This is something what happens as k goes to infinity. Okay. As k goes to infinity, whether this goes to 0 or not. So claim is, so we want to show okay. So what happens to this one? So that is a question of that infinite product. To understand that, we just need to understand one point. So how does cosine of this? I mean, how do we know? We are multiplying numbers less than 1, right? Will it go to 0 or will it not go to 0? Well, that depends on what these numbers are like. But here is the absolutely most important point, that see theta to the n. So here is the key point of PV numbers. So theta, so let's say let P of x equals some x to the power, I don't know, so whatever it is, x to the power d plus a1 x to the d minus 1 plus so on up to a sub d be the minimal polynomial of theta. So, and let other roots. So let's say roots are theta and tau 1 up to tau d minus 1. There are d minus 1 other roots where tau I have absolute value less than 1. Okay, all the other roots are of absolute value less than 1. Okay, so what is the point of this? So here is the point. So look at something like, so theta. So what is theta plus tau 1 plus up to tau d minus 1? It is the sum of all the roots, right? It is minus a1. It's an integer. Agree? What about theta square plus sum of the roots, sum of the powers of the roots? I claim this is also an integer. Why is that? In fact, the claim is that theta to the n plus tau to the n, tau d minus 1 to the n is an integer always. The point, the reason is, okay, here, by the way, so AIs are integers. That's important. So you see the coefficients, this is a monic polynomial, so no division will happen either. The thing is, so why is this true? As I said, I'll just indicate the first couple of them. You'll see. See, instead of this sums of powers, if you had elementary symmetric polynomials of the roots, they would be just AIs. These are what are called power symmetric polynomials, if you know the terms. But if you don't know the term, it doesn't matter. The sum of roots, you know, we have all these formulas for the some elementary symmetric polynomials of the roots in terms of the coefficients, right? So sum of the roots is just minus a sub d a1, which of course belongs to z. Okay, so if you look at the next one, theta square plus tau 1 square plus tau d minus 1 square. What is that? So it is basically the sum of the roots. It is actually, I say that it is the theta plus tau 1 plus, it's the sum of roots minus all the cross terms. Okay, I should now pairwise products. Okay, I don't want to write it, but point is because I should have called this theta. I mean, it's just a bit pairwise products. So this will be minus of a1 squared minus 2 times that the sum of pairwise products is actually a2. So this is also going to be an integer. So and so on. I will leave it for you to check. So if you don't know this, you can check what are called Newton's identities. They are recursive things which express these power symmetric functions in terms of the elementary symmetric functions. Elementary symmetric functions of the roots are going to be the coefficients. Power symmetric functions can be expressed in terms of them. It's kind of clear what you have to do. If you want theta cube plus tau 1 cube plus tau d minus 1 cube, first you take the sum whole cube. That will not only have the sums of cubes, but it will also have things like square of one times another or product of three distinct roots. those will come into, and then again, you can express them in terms of elementary symmetric polynomials and so on. Okay, so is this okay if I leave this? I mean, so it's kind of clear. Is that okay?
Yeah.
Okay, so this is true for all n. Okay, so this is the key point. What does that mean? It means that theta to the n is extremely close to integers. Because so then implies let's introduce some notation, which will be, maybe I will use it later also, equals distance between a number to integers, means distance to the closest integer. Okay, it's either the one below or one above, whichever is smaller. It's a number between 0 to half. Okay, so this is always a number between 0 to half. So then from here, what we get is that if u is the maximum over I, all the magnitudes of the other roots. Okay, so put the absolute values of, they can be complex numbers. Then what is the distance of theta to the n to integers? You know, theta to the n added to this number gives an integer. So the distance of theta to the n from integers is at most this. So what we see is that the distance of theta to the n to integers is bounded by, what is the sum of this? Each of them has absolute value at most u. So u to the n times d minus 1. Okay, so this is decaying extremely fast. This is the point of Piso-Vijayaghavan numbers, that powers of Piso-Vijayaghavan number are very close to integers. Now you see where the problem might come. So when theta to the n is very close to an integer, this is like cosine of 2 pi, and then it's close to 1. So that's why this product doesn't decay. Okay, so let's make that precise. But before that, is there any question about this? This is the key point, how the PV number shows up, that its distance to integers is decaying very fast, exponentially fast. Okay, so now let me go back here and see what that means. Therefore, if you look at, so how do you control? So now consider how cosine 2 pi theta to the n. Actually it is so the claim is, so we have to look at this one, right? N equals 1 up to k. So this is what this is. So the point is that cosine, so here is a key point to understand. Cosine x is like, how does it behave? Like 1 minus half x square, right? Sorry, 1 minus, yeah, it is like 1 minus half x square plus blah 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 as x goes to 0. That's the expansion of cosine. So because of that, what you see is that, and the periodicity, also cosine is periodic. So what I can say is that, so because of this, cosine 2 pi x, if I look at any cosine 2 pi x, I can say it is very close to, I mean, both ways we can write a bound. So is greater than equal to, so do I want to write greater than equal? Yeah, greater than equal to 1 minus. So first of all, look at x going close to 0. Okay, so look at x going close to 0. It is 1 minus, well, 1 minus, what is it? 2 pi also I have to put here. So 4 pi square. So you get 2 pi square x. Well, okay. Cos x is, yeah. So something like 1 minus 2 pi square x square. Okay. But if x is close to some other integer, then it doesn't matter. All that matters is, because of the periodicity, how close x is to an integer. So the claim is, all this 2 pi also we don't need. I mean, so let me just write 1 minus some constant Okay, this is the claim. Is this okay? For x going to 0, it is coming from this power series expansion. You can see it. I mean, you want to write a precise inequality, but that's okay also. You can write, if you want, cosine x is 1 minus half, 1 minus 2 sine square x by 2, and use the inequalities for sine x in terms of x and get this. So, but cosine 2 pi x is behaving like 1 minus x square near x equal to 0. And by periodicity, it behaves the same at any 2 pi x, where if x is close to some other integer, it's exactly the same. So it is 1 minus c times the fraction, the distance to integers square. This is actually the heart of a lot of things, right? I mean, so central limit theorem, this is the whole point. All of central limit theorem proof, when you use Fourier analysis, it comes to this fact that cosine x behaves quadratically near x equal to 0. That's where it comes from. So here we are writing inequality. So we write like this. So it is like 1 minus this one. So because of that, hence 1 minus cosine of 2 pi t to the n, 2 pi theta to the n, which is anyway always greater than or equal to 0 and bounded by the fractional part of theta to the n squared. I mean, not fractional part, distance to integers of theta. By using this 1 minus cosine 2 pi x is bounded by, sorry, there is a constant here. There is a constant which is, you can take 10 or something. I mean, it's a simple constant. It may be 10 or 20 or something like that. Okay, so you get this. But you know that this is actually bounded by d minus 1 times u to the n. So it is bounded by c times d minus 1 square times u to the 2n, which is summable. Which implies that the infinite product converges and is not 0. Because none of the terms is 0. So for it to be any of the terms to be 0, 2 pi theta to the n has to be an odd multiple of pi by 2. But that would require, but then theta to the n would have to be rational. That's not true. Theta is irrational. Okay, if 2 pi theta to the n is an odd multiple of pi by 2, theta to the n would have to be a rational, right? So that's not true. So because of that, this infinite product converges and is not 0. So done. We are done actually. So what this shows is that thus nu lambda hat of 2 pi theta to the k converges to, in fact, this infinite product cosine of 2 pi theta to the n equals 1 to infinity times nu lambda hat of 2 pi, which is not 0. By Riemann-Lebesgue lemma, but 2 pi theta to the k goes to infinity. So by Riemann-Lebesgue lemma, it cannot be absolutely continuous. It's not absolutely continuous, but by the law of pure types, it has to be then singular. Okay, so it is single. So that's the proof.
So Manju, is it really necessary? Okay, I don't. Maybe it's easy, but why is theta not rational? Because anyway, we don't need that, right? To prove that it's not that the terms are not going to be 0, because for finite terms with theta is clear, and then for large terms it's close to 1. So, but why? Okay, first of all, I don't see it.
I mean, that is part of the definition. Theta is an irrational number. Okay, PV number. Okay, if I didn't say it, it's a algebraic integer. Okay, so I don't. Yeah. Okay, PV number is. Okay, I should say it is. I don't include integers here. Actually, I mean, theta is first of. Right. I mean, it is so well. Okay. I mean, so if it's a rational number, it has to be integer. Okay. I don't know in the definition whether they include that or not. Okay. I will have to check. But here I'm taking theta between 1 and 2. And if it is a rational number, if it is an algebraic integer, it has to be an integer, right?
Okay. Yeah. Okay. Yeah.
So
Thanks.
theta is between 1 and 2. So it's not, I'm taking it to be, okay. So maybe, yeah. So theta is, right. That's why theta is irrational. Yes.
Okay. Yeah. Thanks. That's
Yeah,
better.
you're right. I don't know what is the convention, whether one includes in algebraic integers, I suppose integers are included, but whether PV numbers you also include them, I am not sure. Maybe. Any other questions, comments? So if there's something not clear, I'll be happy to explain. So this is a beautiful proof. Okay. So the key point in the way in which these PV numbers show up is that they are powers of the PV numbers are very close. See, basically what happened was this: when you evaluated, this is itself is a clever step where you want to evaluate. But suppose you evaluate, you get this. Basically, there are two things. If you look at this one, just to at the cost of over explaining, there are two infinite products here. One is, okay, if you just let k go to infinity, as k goes to infinity, you have one is n equals 1 through infinity cosine 2 pi theta to the n. The other is n equals 1 through infinity cosine 2 pi divided by theta to the n. That is this one. Now, this one converges is okay. This is okay. This is convergent because that is theta to the n. But the question is what happens to this part where theta is bigger than 1 and it is going large. That can only be convergent to something non-zero if you see, if too many of these cosines are less than 0.9, then you already get something vanishing, right? So the only way this product doesn't converge to 0 is that most of these cosines have to be close to 1. Very close to 1, and for that theta to the n has to be very close to integer. So that is how you see that theta to the n being close to integer is kind of necessary for this to work, and that is what is given by the piso numbers because of this algebraic identities, that theta to the n plus the powers of the remaining conjugates are integers. Okay, so
maybe obvious. Maybe obvious, but I guess there are countably infinite number of PV numbers. Maybe that's obvious.
It's not okay. Yeah, it is true. It is not obvious. I think one needs to argue that. Yeah, you're right. So there are I mean, we want to say even there are countably many in 1 to 2. I think okay. I now don't know the proof for that. It's not a complicated proof. I have seen it, but I now cannot recall. What we want is so. Okay, but let me just mark it here. I should at least include it in notes. I don't think I'll come back to it. You mark. So countably, of course. The total number is countable, but this is a point that one has to actually fill in. Yes. Okay. Any other thing? So one of the things here is that we didn't need it to go so fast exponentially, right? So one may ask here, maybe, I mean, there are other numbers, right? I mean, what if I find some other? So this piso numbers had this nice property that the distance to integers goes exponentially fast. But what did I need? I only needed for this to what did I need? For this to converge and not 0, what I need is the summability of this, right? That is enough. That is like much weaker than exponentially decaying. So can we get other examples? I told you that there are no other known examples, but here is a fact. Some facts about piso numbers. So this is first fact, which is relevant to what I said above. So this is due to Piso himself, I think. suppose theta is some number bigger than 1 and let's say summation t times theta to the n. Distance to integers. Sorry. So take theta to theta bigger than 1 and t is real number and this is summable. Then theta must be Peso number. Okay. There is also a fact about t. It has to be in the what is that algebraic extension of q theta or something like that, but we don't need that. But point is, if this happens, so here what I needed was something like that, right? So t is whatever. I mean, I did not have to take 2 pi times theta to the k. I could have taken 2 pi t times theta to the k. It doesn't matter. What I require here is something like this, theta to the n times something. The distance square is finite. So you see that if it is true, even if you assume just that, you see that it's PV number. So it's not that, although there is looks like a gap between this and this, whenever this is summable, this is actually a PV number. Okay. So, and second is, this is an open question actually. If theta is bigger than 1 and distance to this goes to 0, or even with some t times, etc., does that imply theta is a PV number? So we don't know. I mean, it's an apparently open question still. The thing is, I mean, of course, it's not going to be of help to us anyway. Even if it is, it's not. We need a certain slight quantitative thing here that it should be. This should be summable. But it's a natural question. Are these the only numbers which are really this close to integers? Can I find some other numbers whose powers are kind of very close to integers? Apparently, it is not known. But there are, so it is known under 2 cases. This is one known case. Meaning that you just don't assume theta to the n goes to 0, but you assume that it is actually summable. Then it is true. But another thing is, if a priori you assume we know theta is algebraic, integer, then also apparently this is known. I haven't seen a proof. I mean, there is a book by Salem. If this type of thing interests you, I can give you a reference. I mean, it's so Salem has a book called Algebraic Numbers and Fourier Analysis. Salem worked a lot on these type of things. So it's there all these various things are studied. So algebraic numbers and Fourier analysis. So it is all about this kind of stuff, how they show up in. Now it is a kind of standard connection, but I think when Erdash made it, it was something stunning. Okay, so that's about it. What else do I want to say? Yeah, so one question is, okay, so we didn't show. Okay, we have only shown cases where it is singular. Maybe you will think that what about absolute continuity? We didn't show any case where it is absolutely continuous, right? Except half. Okay, so we have only shown I mean, no need to have even shown that. Nu half is absolutely continuous. So maybe that is one anomalous case. Maybe there are no other things. So there are two types of things in this direction. Okay, two kinds of results in this direction. One is explicit numbers for which nu lambda is absolutely continuous. So you take some specific lambda and show that it is actually absolutely continuous. It so happens only countably many examples are known so far. Okay.
By countable, you mean countably infinite or countable?
Yeah, it is countably infinite. In fact, I will show you countably infinity in a moment, but that's not the full set for which it is known. There are countably many examples which is known. The reason I mentioned that is to contrast with the second one, that for almost every lambda in half to 1, here almost everywhere is with respect to Lebesgue measure, nu lambda is absolutely continuous. Okay, so this is a result of Solomiak, proving a conjecture of Garcia or some, that's what he says. But let me just say, improving on Erdős. So I said Paul Erdős proved that theorem that we proved in 1939. In 1940, he has a paper where he showed that. So Erdős, what he showed is that there exists some delta positive such that for almost every lambda in 1 minus delta to 1, nu lambda is absolutely continuous. Okay, that's what Erdős showed. That delta was, I mean, that was something non-explicit and something like 0.99 or something like that. So, but what Solomiak showed is that you can come all the way to half. In the whole range of interest, half to 1, it is absolutely continuous. Well, it is a kind of weird thing that happens time and again. It's very weird when you see it first, but then you get used to seeing this kind of stuff, that you know that most lambdas work. But if you ask to produce lambdas, at least here you can produce countably many. There are situations where you know that it happens, something happens for almost every lambda, and you don't know a single explicit example for which it happens. That is called the power of the probabilistic method. But okay, so these types of results are there. So this one is what Kaushik was asking, how difficult shouldn't we prove one of these results? I mean, actually, this is also Fourier analytic proof, actually. Okay, so how do you show that it works? So one way of showing absolute continuity is if the Fourier transform is in L1, right? So you remember this gap. Riemann-Lebesgue lemma says that if your measure has density, then its Fourier transform must go to 0. Whereas to come back the other way, you need slightly more. If the Fourier transform is in L1, then you know the Fourier inversion formula works and you have a bounded density. So this proves proceed by that. But there is, of course, not entirely trivial, because you don't work with fixed lambda. You work with almost every lambda. How does that show up? So I was thinking whether to do it or not, but maybe I will just leave it. Okay. I will leave it. But what I want to show is some examples. So here we will show something that was done before by Wintner. So I'll show you examples. So Wintner, 1935. This is same Wintner we see in probability in law of iterated logarithm and so on, Hartmann, Wintner, and so on. So Wintner showed that when lambda is 2 to the minus 1 by k, k greater than or equal to 1, then nu lambda has a density. That is, in fact, in C, k minus 1, I think. K minus 1. So when k is 1, no, it is not continuous. So yeah, this is what actually Vintner writes ck minus 1, but I don't understand how. So I will just claim ck minus 2. Okay. Or well, what does that mean? Okay. So when k is for k greater than equal to 2. See, when k is 1, this is 1/2. When it is Lebesgue measure, uniform, right? So that is not continuous. So where c k minus 1 means c super 0 should be continuous function. So I don't know why he writes ck minus 1, but okay. I will only say it for when c0 means continuous, c1 means once differentiable, continuous, and so on. Okay, so let's do this. This is actually very easy. So let lambda be 2 to the minus 1 by k. So fix that. Okay. So let's write new lambda hat of t, which is n equals 1 to infinity cosine lambda to the n t, right? So let's write n as, let's write n in modulo k. Okay, so n we can write as m times k plus r, where 0 less than equal to r less than equal to k minus 1. So we'll write like that. So then I have product over r equals 0 to k minus 1. And then the product is over m equals 1 to infinity. What I have here is cosine of, yeah, what is lambda to the n? Okay, so lambda to the n is here 2 to the mk plus r minus 1 by k, right? 2 to the minus 1 by k raised to the power of n. N is like this. So which is 2 to the minus m plus r by k. So let's write like that. Cosine of 2 to the minus m into t times 2 to the r by k. Is it okay? I just divide it into to k equivalence classes. Just you sum over periodically. 0, n goes from 1, k plus 1, 2k plus 1, etc. You group them. Then 2k plus 2, 2k plus 2, etc. You group them and so on. So that's how we have grouped. But the point here is that, do you see what this is? What is this? This quantity. Yeah, what is this? You think of this as fixed. S is t times 2 to the r by k. Cosine of 2 to the minus m times s. What is that product? It is nu half Fourier transform at t times 2 to the minus r by. I think I had a minus here. I forgot. Minus r by k. Right? That's nu half. Nu half is with 1 by 2 to the m will come. Right? So that is what you get. So what you see is that thus nu 2 to the minus 1 by k is convolution of k scaled versions of Lebesgue measure. So by the way, what is nu half? Nu half is Lebesgue measure, uniform measure on minus half, minus 1, 1. So what is nu half hat of? Nu half hat of some a times t is Fourier transform of Lebesgue measure on normalized Lebesgue measure on a scaled interval. What is that scaled interval? It is minus AA or minus 1 by AA, something like that. So the scaling, you can quite easily see it is just a matter of scaling the interval. So when you take nu hat of AT, this is true for any measure actually. if you take nu hat is measure nu hat of A times t is the Fourier transform of a scaled version. So what we have here is that nu 2 to the minus 1 by k is convolution of k scaled versions of Lebesgue measure. And it is an easy fact that if you, okay, so there are two ways to go about here. One is when you convolve measures, it will be nice. So you start with Lebesgue measure has density, which is not continuous because it's a step function. But if you convolve, you get density. So if you convolve 2 times, you get a continuous density. When you convolve uniform measure with another, let's say, so this is one density and another density is, let's say, on a scaled interval or something like that. When you convolve that, you will get a, I mean, if they were the same, you would get a triangular density. Here also you will get something which is continuous. If you convolve it one more time with a uniform, you will get a C1 density and so on. So hence we get that it has Ck minus 2 density. So that's the proof. Actually, let me tell it another way. If you are not clear, if this is not clear, let us do it another way. Very easily, because so that is actually, so here is another way. If you don't, if you are not yet familiar with convolutions and this fact that convolution will lead to smoothing, which is a very important point. I mean, I can leave it as exercise, but here is another way to for us to go about. We know that nu half is uniform, right? Nu half hat of S is actually sin S by S. We know that. The Fourier transform of Lebesgue measure on -1, is sinc function. So this is actually product r equals 0 to k minus 1 sine of t times 2 to the minus r by k over t times 2 to the minus r by k. So which is overall big O of 1 over t to the power k as t goes to plus minus infinity. Right? Because sine is bounded, this is anyway fixed. So this behaves like 1 by t to the k. And you see that, therefore, hence, if the Fourier transform decays, then hence t to the k minus 2 times nu is in L1. Right? I mean, 1 by t square is integrable at infinity. That's why I don't take k minus 1. So implies nu 2 to the minus 1 by k has Ck minus 2 density. That's the other way to see it. If you don't want to talk about convolutions, here is another approach. This is where Wintner writes that from this, we see that it is Ck minus 1. I don't understand how he says that. Okay, anyway, it's okay. So we'll get this. Is it okay? Any questions here? So for all this, so you can see countably many numbers for which it is absolutely continuous. But in a way, it's cheating because it's actually convolutions of the half measure. Well, after scaling, that's what it is. So if you understood this proof, let me give a small exercise. So use Erdash or Solomiak to show that for any k, there exists a delta k positive such that for almost every lambda in 1 minus delta k to 1, nu lambda has a Ck density. Okay. So what I mean is this. So Erda showed that there is a delta such that for almost every lambda in 1 minus delta to 1, nu lambda has density. That's all. Has density. I'm now saying that show that it will have a Ck density. So of course, don't start from scratch. One is you should use Erdash result. You should assume Erdash result, and then you should think about this proof. Then you will get it. Okay, so that is about Bernoulli convolutions. So So as I mentioned, there are other examples known. Garcia has some bunch of examples, again using some algebraic properties. Now I don't remember, but the assumptions were somehow a bit like the opposite of Piso numbers. So he found a bunch of theta for which, for a bunch of lambda for which nu lambda is absolutely continuous, and the assumption on lambda or 1 by lambda was that they were somehow in the opposite direction of Piso numbers. The conjugates were bigger than 1 in absolute value, some things like that. I don't remember the details, but still there are countably many examples known of absolute continuity. Okay, so maybe I will now 12:58. Maybe I'll just stop. I will not do the other part, which is the R' result. Okay. Yeah, so I think I will end here. So next time we'll go to a different application.